Hello everyone. Today we shall discuss about viscosity, Stoke's law and terminal velocity. You see here what we can discuss with this is that of the physics of falling spheres in fluids. You see here this is a sphere ball, right? You can see that the viscous drag dominates at low RE. Here you can find that this is Fg, right? At terminal velocity Fg equal to Fd plus f of b, right? The terminal therefore we are getting that this force will be equal to this force and this force. That is Fg equal to Fd plus Fb. Here you see Fd, it is Fd is equal to viscous drag, and that is equal to 6 pi eta Rp according to Stoke's law. So we will learn all these relations. First of all, we have to know that f of g is equal to f of b plus f of d, and here we get f of d equal to 6 pi eta Rp according to Stoke's law, and this is the introduction of fluid dynamics. Here I have taken a scale as 1 centimeter is equal to 0.005 meter. The next one what we get is, you see here the next page we will define the environment viscosity eta. Here we have taken honey, it is low eta, that is viscosity, and high eta, higher viscosity, means greater resistance to motion. Viscosity is a fluid's internal resistance to flow, essentially its internal energy, internal friction. Viscosity is a fluid's internal resistance to flow, essentially its internal friction. The fluid fights back viscous drag. When a sphere moves through a viscous fluid, the fluid exerts a resistive force opposing the motion, and this is the viscous drag force. You can see here that this is the viscous drag force. The force is not static, it increases as the interaction between the fluid and the object intensifies. So the force is not static, it increases as the interaction between the fluid and the object intensifies. Quantifying resistance, Stoke's law. This Stoke's law is given by F equal to 6 pi eta Rp, where you can get that fluid viscosity is eta. This one is fluid viscosity eta, and here you can find that the sphere of radius is r, and the velocity is, this is the velocity, right? So you get Stoke's law calculates the specific drag force on the sphere. Note the linear relationship. If you double the speed, you double the drag. So F is equal to 6 pi eta Rv according to Stoke's law. The conditions for validity. It is valuable for laminar flow but not for turbulent flow. A smooth, rigid sphere. The sphere should be rigid and smooth. A small object scale. Laminar flow, low Reynolds number. The Reynolds number should be low here. Stoke's law applies to creeping flow, motion that is slow and orderly. It breaks down if the fluid becomes turbulent. So you have to remember that Stoke's law is always applicable in laminar flow but not in turbulent flow. This is the conditions for validity. And laminar flow is smooth, rigid sphere, a small object scale, and laminar flow that will be low Reynolds number. Phase 1, the drop static force. You see this is the buoyancy Fv, force of buoyancy, and this is the weight. This sphere is released. Gravity pulls it down. Buoyancy offers a constant upward push equal to the weight of the displaced fluid. Since weight is greater than buoyancy, the object accelerates downward. We know this according to Archimedes principle, right? The sphere is released, gravity pulls it down, buoyancy offers a constant upward push equal to the weight of the displaced fluid. Since weight is greater than buoyancy, the object accelerates downward. We see that why this is equal. You see in the first case we got this equation that this one that is force of buoyancy. Fd is a viscous drag. Fd is a viscous drag and the force of buoyancy, and that is equal to F of G, right? In this way, again, the force by gravity, that is F of G, that will equal to force of buoyancy plus viscous drag. That is important for viscosity and Stokes' law and terminal velocity. Now we'll get another important thing, that is this one that we are going to discuss, Stokes' law. That is the conditions for validity, and this is the phase 1, the drop or static forces. Now drag enters phase 2. This is acceleration. When the phase 2 exert, we get an acceleration, that is viscous drag. As velocity increases, Stokes drag F equal to 6 pi eta Rv kicks in. The faster the sphere falls, the stronger this upward drag force becomes. Right? The faster the sphere falls, the stronger this upward drag force becomes. So in this case, what we get, force of gravitation is equal to force of buoyancy plus force of viscous drag, d. F of d or viscous drag, we can say this one. So what we are getting here, as this is the phase 2, as velocity increases, Stokes drag F equal to 6 pi eta Rv kicks in. The faster the sphere falls, the stronger this upward drag force becomes. Phase 3, equilibrium, terminal velocity, and at the phase 3 there will be equilibrium, and that is there we will get the terminal velocity. That is, see here, weight W is equal to force of buoyancy plus and viscous drag, right? So if force on downward and force is upward, that is same. Eventually the upward forces perfectly balance gravity. The net force becomes 0. Acceleration stops. The sphere continues at a constant maximum speed, terminal velocity, right? So in this case, the force in upward direction and force in the downward direction is 0. When the force is 0, the ball moves with a constant velocity. The ball moves with constant velocity in the liquid, and the maximum velocity, and this is constant velocity, is known as terminal velocity, or what we call it as Vt. Now in this case, what you get here, you see here that is derivation, step 1, the force balance. What is that? Weight equal to buoyant force plus, I already told you that weight, the force of weight is equal to the force of buoyant force plus viscous drag. See this one, the weight equal to buoyant force plus viscous drag. And what you get here is this here, weight equal to buoyant force plus viscous drag. Weight equal to mg and force of buoyancy, m of fluid into g, mass of fluid into g, mass of fluid replaced into g plus 6 pi eta r v. Vt, that is Vt is the terminal velocity. To find the formula for terminal velocity, we translate our equilibrium diagram into an algebraic equality. So what we get, mg is equal to m, mass of fluid, displaced into g plus 6 pi eta r Vt, where Vt is the terminal velocity. And here you see that derivation 2 introducing density. You know that sigma, the density of a sphere, rho, density of fluid, the volume of the sphere equal to 4 by 3 pi r cube. So replace mass with density and volume. So replacing the mass with density and volume, we get sigma v into g, rho v into g 6 equal to plus 6 pi eta r Vt, terminal velocity. We rewrite the weights in terms of object's density and fluid's density, right? So we are getting this value, that sigma Vg is equal to rho Vg plus 6 pi eta r Vt, where Vt is the terminal velocity. Now we will get from here that derivation 3, isolating velocity. So we are getting 6 pi eta r equal to sigma minus rho into v into g, right? So 6 pi eta r Vt is equal to sigma minus rho, and V is 4 by 3 pi r cube, that is the volume of the ball into G, 4 by 3 pi r cube, right? So you are getting this cutting pi will this value will cut, right? So by grouping the densities and cancelling out common terms pi and 1 factor radius, we solve for Vt. So what you are getting, you see here 6 pi eta Rv, right? That is 6 pi eta R Pt. That is going to sigma minus rho into 4 by 3, that is the volume 4 by 3 pi r cube into G, right? So this radius will cut out, right? So this radius will be cut and this will be 2, this will be 2, it is given here also, right? So what you are getting at the end, you can see that this equation becomes Vt equal to the master equation or terminal velocity. In the terminal velocity, what you get Vt to r square sigma minus rho G 9 eta. From where you get, you see in the previous equation, this one 6 pi eta r Pt sigma minus rho 4 by 3 pi r cube G, right? Let us find this one 6 pi eta Rv. From here we get 6 pi eta Rv is equal to 6 pi eta Rv is equal to sigma minus rho 4 by 3 pi r cube G, sigma minus rho into 4 by 3 pi r cube into G, right? So if we calculate this one, we can get the value of Vt. So Vt will be given by, you see here, this number is given by 4 divided by 6 into 3, right? So 2, 3 are 6, 2 days 4. So the number is 2 by 9. We are getting a value 2 by 9, and this one is written as this one r, and r will cut, it comes to r square. So 2 r square sigma minus rho G by 9 eta. This is the terminal velocity. So what you get, this equation dictates the maximum speed. It is the mathematical conclusion of the battle between gravity, buoyancy and viscosity. So this is the final result that we are getting, the terminal velocity Vt equal to 2 r squares rho sigma minus rho into G divided by 9 eta. And what you get, this equation dictates the maximum speed. It is the mathematical conclusion of the battle between gravity, buoyancy and viscosity. Now you see here analysis, the viscosity factor. The Vt equal to 2 r square sigma minus rho G by 9 eta. Viscosity is inversely proportional. Velocity, terminal velocity is inversely proportional to viscosity. See this factor. Thicker fluid, higher eta, lower terminal velocity. Thinner fluid, lower eta, higher terminal velocity. You see, this will be the graph. When the terminal velocity, when the viscosity is high, terminal velocity is very low. Right? So in this factor we get that the Vt is inversely proportional. The terminal velocity is inversely proportional to eta. Eta is the viscosity. If the viscosity is more, terminal velocity will be less. Here see, when the viscosity is more, terminal velocity is less. When the viscosity is more, when you can find that when the eta is less, this is less, the terminal velocity is more. So the graph will be like this. This is the graph of viscosity factor, right? For that there is other important thing, that is analysis the radius factor. Here Vt equal to 2 r square sigma minus rho into G by 9 eta. Sphere is A r, sphere B 2r, radius 2r, speed is 1x, speed is B 4x, because it is Vt is directly proportional to r square. This factor, well, r square, right? So it will be 4 times. Velocity scales with the square of the radius. A sphere that is twice as large will fall 4 times faster, right? So we getting the radius is doubled, then it will be 4 times, because it will be 2 in r into whole square, that is 4r. So the velocity scales with the square of the radius, sphere that is twice as large will fall 4 times faster, right? And the summary notes, what do you get the summary note? Viscosity. Viscosity means internal frictions or resistance to flow. Notice Stoke's law, F equal to 6 pi eta rp, drag force in laminar flow. And terminal velocity is given by Vt is equal to 2r square sigma minus rho g divided by 9 eta, where Vt is the terminal velocity, r is the radius of the sphere, sigma is that sigma is the density of the solid, and rho is the density of the liquid, g by 9 eta. This is the terminal velocity. Key dynamics: motion stabilizes when drag plus buoyancy equal to gravity. Motion stabilizes when drag plus buoyancy is equal to gravity, nature 6 equilibrium. And the end what we get at nature 6 equilibrium. Thank you everybody for watching this video.